So now let's look at applying control to our process. And what we'd like to accomplish is that our process, that its state variables, remember, these are the important things that we'd like to prescribe values for. So for instance, the concentration and temperature and pressure and so on, we want to achieve specific values for those. So we'll define those specific values as set points. So there are set point values that we want our actual process to get close to. And so we can define a useful function, namely the error. We can think of it as an error when our process is not lying on the set point, on the desired set point values. So we go ahead and define the error E of t in this way. So the set point, that is the value we want our process to achieve. So if we imagine going to our controller on our unit and we type in deet, I want pressure of 5 atmospheres or whatever it is. So that's going to be a constant. And our current value might be different. So it might currently be 2 atmospheres. And if it's a well-designed controller, then the pressure will start to go up. And so this will go up 2 atmospheres, 3 atmospheres, and hopefully it gets to the set point 5 atmospheres. So the reason I'm saying all that is just to emphasize this is a time function. We know the state is changing in time. And so as that changes, then the error changes as well. So we hope that the error gets closer and closer to 0. And towards this, we can define 3 types of controllers. Well, we can define any number of controller types, but the ones that we'll consider are these 3. So a proportional controller is the type where we want our control action to be, we want that the control action would be in proportion to the error. So there'll be some constant times the error. So remember, this is the control action is, for instance, a flow rate somewhere. And we are saying here that the amount by which we change the flow rate is related to the amount of the error. And so if there's a small error, then we don't need to take as much control action. If there's a larger error, then we try to take more control action. So that's the case of a proportional controller. So we say the control action is proportional to this difference, which is the same as proportional to the error itself. Then we could say, well, in a proportional controller, unfortunately, what might happen is as we get closer and closer to the set point, in other words, as the error gets smaller and smaller, then we are taking less and less action. And so we might never actually get onto the desired set point. So to ameliorate that, we, instead of only looking at a proportional control, we also add up all the differences. So we look at from the time we started exerting control to the current time, how long has this error persisted? So we integrate the error as a function of time, and then that gives us a sense for, is there a persistent offset? So in the proportional part, we wouldn't necessarily account for that because according to the proportional part, everything is fine. There's a very small error, so there's not much to do. Whereas in this new term now, if there is a small offset, as time goes on, this is the integral in time. So as time goes on, this term will get larger and larger. And so this will again force us to take action if there is a small persistent offset. And we can, of course, rewrite this in terms of the error function. So that's ET there, and this is the integral of ET there. It might also occur to us, well, what happens when we do take enough control action, but now the integral is still going up? So even after we get onto 0, this integral doesn't go to 0. Well, in that case, when we do get onto the set point, then we just change the lower limit here. So the limits are not shown, but in principle, it's from t0 to the current time t. So we just update that t0, the lower limit, to reflect the time when we did get onto the set point exactly. So there is some resetting required here if we don't want the historical error to force us to keep taking control action when we don't need to. Right, so that's the PI controller, proportional integral, right? We've got some integral action here. And we can see also there is an additional constant, 1 over tau I. And you might wonder why this weird 1 over tau. And we'll see later, it's more convenient to write it as a 1 over tau. And in fact, most of the time, this should be a capital I. So that's our PI controller. The KP is still out here. We keep that KP as multiplying everything, right? So that's the form, the standard form for a PI controller. Then for a PID controller, we are in effect trying to get ahead of the curve, right? If you think about these two controllers, they are kind of retrospective. So they wait for an error to exist in the first place. Whereas we could say, well, I think I can do better than that. I can anticipate an error emerging, and I can act to prevent the occurrence of the error, or I can anticipate how much the error is going to grow by and try to avoid that error growing in the first place. So we can do that by looking at the derivative. So currently, how much is the error growing? And so we can take action based on our current observation of the growth in the error. And so the growth we can estimate through differentiation. We can say, what's the rate of change in time of my error? And I want to take action against the growth of that error. And again, we have a constant to control how much we want of that kind of action. So that's how we can think of these constants. They control how much of that that aspect of the action, how much strength we give to each of those aspects of the action. So those are the three types of controller. And as we've seen several times now in our state equations, when we Laplace transform those equations, we also have to transform the controller because we are going from the t domain to the s domain. And so we can look at, for these standard forms, for the p controller, we can define the Laplace transform of the error function. So as we said, the error function is in the time domain. So if we Laplace transform this, then we'd have the E of S version. And you could say, well, this is a constant. So currently we've chosen a constant set point we want to achieve. So the transformation of a constant is the constant divided by S, and then this would be some other function. So we could do that, but just for convenience, we don't actually, we'll just say there's some function E of S that will happen. So when we transform these equations, the left-hand side, that's simply U of t, so we'll just call that US, and then the error we'll just call ES. So for the proportional part, we can see that's simply going to be KPES. For the PI controller, we can see here it's going to be ES, and now we've got this integral. And as we showed last time, the integral part will take a 1 over s times the function itself. So it's 1 over s times ES. And in this case, we also had a 1 over tau as a constant. So there's the 1 over tau and then 1 over SES. So that's what we have in the case of the PI controller. And what we could do is group out the ES. So we've got ES for both terms. So we just group that out. And now you see the beauty of the transformation, right? We don't have an integral now. Because of this property that the Laplace transform of an integral is just 1 over s times the function itself, we don't have to have this this other type of operation. We can still stick to pure algebraic functions here. So there's no integral that occurs in the Laplace version of the equations. So in contrast to here, you have to contend with an integration. So here you don't. So the equation is much simpler. And you can also start to see why we introduced this as 1 over tau I, right? Because if you take this one and put it in the numerator here, then we're going to get tau I s plus 1, right? So, or in fact, let's do it as a new part. So this was what we had written there, and I'm just going to copy this out. And here this, I'm taking the 1 into the numerator of the other term. So I need to write then tau I s plus 1. And this one, I'm just moving the s to the standard position. So times s here. And now we can start to recognize this. We've seen forms where we had tau I s plus 1. So if we look earlier at our Laplace transformations, we said that in the standard form for a second order, for instance, we had a form like this, right? We said for higher orders, we get that. And for second order, we had a form like that. So we can start to see that for the PI controller, we are getting closer to a standard form as well, right? And we like standard forms because they behave nicely and they let us, when we propose a framework, then everything performs within that framework in expected ways. So that's a nice standard form. Then trying to apply the same approach to a PID controller. Of course, we can, we just have the additional term here with the derivative. And again, we had established a Laplace transformation of a derivative. So we had said that for a derivative, we get S times E. And so for the PID controller, we just have this additional form here. And again, we can seek a standard form for this. And in fact, it is done here, right? So these just summarize the same things that we've said now. If we write it in terms of GC. So instead of writing it as U's and E's, if we define GC to be U over E, then GC takes these forms. And yeah, the standard forms, so this one is already, well, this is so basic, there's no standardization to do. For the PI controller, we just showed this already. And now for the PID controller, as we say, we have this extra term. And what we can do is take everything into the numerator space again. So let's put everything under or over a denominator of tau IS. So we'll have from the 1 here, we'll have a tau IS to keep it as 1. Then this one has a 1 in the numerator, so we keep the 1 here. And then for tau ds, to take that into the numerator space, we will need to multiply by the denominator. So we'll get here tau d tau I, and then an extra s, so that gives us an s squared. And then we can recognize that this is a quadratic expression, and so we can factorize this. So we can say the roots of this numerator will be s plus, the root here is going to be s, and in fact, I think this should be a minus here. So s minus, and then it's minus, I think that's supposed to be a 2b, minus 2b plus minus, right? So the b part here, it's the coefficient of s here, right? Remember, in the standard form, it's ax squared plus bx plus c. So your a part is tau d tau I. So we'll see in the 4ac part of 4 tau d tau I. The b part is a tau I. So yeah, it's going to be a tau I squared. and then the 4AC, C is 1. So we can just check we've got the standard quadratic form here. And then over, what is it, 2A. So 2A is 2 times tau d tau I. So those are the roots of the equation. And so if we just define A and B to be those 2 roots, then we recognize we have a form like this. And if we think about this form, we can rewrite it. If we let tau 1 be 1 over A, then we've got tau 1 times S plus 1. And if we let tau 2 be 1 over B, then this is tau 2 S plus 1. So we can rewrite the whole equation like this. And of course, we've retained this. So the denominator here, tau IS and the Kp, we also have to extract that here. So that's our GC. Okay, so that's what it looks like for the PID controller. So that contributes this additional term to our system. And so for these 3 forms of controller, we have this general relationship that there's some control action, and depending on the controller we've chosen, the form of GC will change, and so GC times the error will be the control action that we must take.